But first, to a man who is responsible for the design and construction of key component at the Large Hadron Collider at Cern in Switzerland. Professor Val O'Shea was one of those behind the Atlas detector at Cern, one of the devices which found the elusive Higgs boson particle, a discovery which won the Nobel Prize for Physics only last year. And as you've seen there, he's in our Galway studio. Val, good morning to you.
Good morning, Anthony. How are you doing?
I'm very well. Listen, thanks for joining us. You're originally from Cork, are you?
Yes, a long, long time ago.
So how do you get from Cork to Cern?
I think it was probably luck. In actual fact, my project supervisor at the university there did his PhD with an Italian at Santa Cruz, and the Italian was looking for an engineer at the time to work on some stuff for him at Cern. So I got in through that route, which was really quite lucky.
And the device, or the device you were involved in creating, was the Atlas detector at Cern. Just explain to us what that did and what its role was.
Okay, so Atlas is one of the two general-purpose detectors at Cern. It's the largest scientific endeavour, certainly in particle physics, that's ever been undertaken. It consists of a collaboration of 3,500 physicists, so the author list for each paper is 18 pages long. The detector itself is one of two general-purpose detectors, 7,000 tonnes, 45 metres long, 25 metres in diameter. And in Glasgow, we built part of the central tracking detector. So if you think of a high-energy experiment as a type of snooker game where you have these protons that collide one with the other, then the tracker in the centre detects all the debris from these collisions with great precision, and it's all done in a very high magnetic field. And then you can measure the energy of each of these elements of the debris and reconstruct a so-called event, what actually happened in the collision of the two protons. So
and it then detects what's created, is that what it does? Well,
the Higgs has been estimated to have a lifetime of 10 to the minus 22 seconds, which is very small. And you don't actually ever see the Higgs itself, you see what it decays into, okay? Because of the rapidity of that decay. So the detectors measure these decay products, and the problem is that only one in every million events will be a Higgs, and that its decay products also happen from other processes. So you're not really looking for a needle in a haystack, you're looking for a particular blade of hay in the haystack.
Whoa. And the success it has had, and winning the Nobel Prize for the physicists last year, and the coverage it's given to science must be a very positive thing from a point of view of getting people interested in science.
Yes, it has a hugely positive effect in that regard, although if one looks at what the effect it might have in society at large in the near future, this is rather more difficult to answer. I do hope it motivates more young people to get involved in science. But as I say, it's a very abstract thing.
And you were at a speech last night in Trinity College. I know you're in Galway this morning, but it was an Astronomy Ireland event. So what was the feedback from people at that?
The material that I covered last night was rather less to do with the pure physics and more to do with the technologies that have been developed in order to make these detectors, and also what sort of possible spin-out that might have in terms of creating a benefit for society in the rather shorter term. I mean, one of the issues with these blue skies research discoveries is that it typically takes many decades for them to filter through to some use. For instance, the discovery of atomic physics enabled the Semiconductor Revolution, which has given rise to all of the stuff we have today. And there's an interesting quotation attributed to Michael Faraday when he was asked by William Gladstone why he was mucking about with electricity at the start of the 19th century. And his reply is, "Someday, sir, you may find a means of taxing this." So...
And I know you're based in Glasgow and University there. How much time would you have spent in Switzerland at Cern and the Collider?
Okay, I've worked on Atlas since 1992, so for
that long.
22 years. Yeah, more or less since its formation. I've lived in Switzerland for 6 years, and I spend an average of a week a month there still.
Oh, so it's real sleeves rolled up involvement.
Yes, of course. Well, now I don't actually work on the Atlas experiment anymore. I work on an upgrade for this because they're going to make the machine 10 times more difficult to work with but produce 10 times more physics, and therefore we need to have new techniques for making a detector operate in that harsh environment.
All right, so it's not all over there. Operations are still going on, are they?
Atlas is foreseen to take data until 2030.
Oh, that long, right, yeah.
So the life of the experiment is of the order of 40 years.
All right, so it'll be continuing.
And it's more or less changed the way particle physics is done, because in the 60s and 70s, one person could dream up experiment, design detector, take data, do the analysis. Now we don't have that sort of possibility anymore, and in actual fact it has maybe a negative effect on the overview that we give people we train in the field.
Okay. Professor Val O'Shea, thank you for talking to us. We'll let you get back to your work.
Thank you very much, Anthony.
Soon. Thank you.